Welcome everyone to today's presentation, Digital Twins for Materials and Structures. My name is Jörg Anger and I'm from the Bundesanstalt für Materialforschung und Prüfung in Berlin. If you look at different structures, be it a space shuttle, a bridge, or a Formula One car, in all those cases, it's very expensive to design a structure a priori, then build it, perform tests with different load configurations, and then just based on experimental data, redesign the structure and perform the cycle again. So in many cases, it's really beneficial to have a simulation model that allows you to understand what is happening in practice, investigate different, say, scenarios, configurations, perform the optimization based on that, and then you can go back to the design and use that. In addition, it's possible to use that digital twin of such a structure during the lifetime of the building or the structure to improve maintenance or analyze the current status, the performance, remaining useful life, and so forth. So we at BAM are interested in issues related to safety of structures. This is an example of a concrete slab under explosive loading, which can be generalized to a building under, say, terror attacks. Now, the question is based on such a lab experiment, or this is kind of outside, but how can you generalize that to apply that to real design buildings? Because you don't want to redo everything. So this is what you do with a numerical simulation. And in this case, it's a combined CFD model for the explosive part and then a continuum mechanics problem for the structure. And you would like to design and analyze existing buildings under different explosive load scenarios. So what you have to do, if we come back just to the mechanics problem, for example, so you would like to understand how this concrete slab is behaving. And so for that, you perform a couple of tests in order to calibrate or identify the model parameters or even set up your model. And so some of the ideas that we have is using replacing different load configurations. You have to do shear, tensile, compression tests by a single complex experiment. And that even allows you to efficiently analyze localization phenomena. So if you have a crack, you usually don't know exactly what is happening. And so based on that CT data scan, you exactly know what the crack is and you can compute what are the cohesive forces transformed through the crack. And if you have a large number of data set, you can perform a statistic analysis in order to get something like a distribution of your parameters. And that allows you at the end to do some reliability analysis because every single setup is different. Now, what I would like to talk about today is, first of all, a little bit about the challenges that we face when we perform modeling. Then I would talk about model calibration, and then finally I would come to digital twins, the applications and challenges that I see, and I'll show one example that illustrates how this can be applied in practice. Now let me start with the modeling. So if we're interested in coming from this concrete community, so if we're interested in understanding how our structures work, there's lots of different phenomena that are interacting. Usually people just start from the mechanics part, so stress-strain relations. In the simplest case, it's a linear elastic model, and then you perform some design of your structure. But reality is, in particular, if you're interested in failure scenarios, that there are lots of different phenomena that are interacting. First of all, there's the moisture transport in porous media. If you look at tunnel, many issues are related to temperature, like fire scenarios, and in many cases there's an interaction that leads to high gas pressures within the porous media that actually leads to something like what we call spalling phenomena. So the the cover, due to the gas pressure, spalls, and then the reinforcement is exposed to the fire scenario and the high temperatures. And then finally, we have this, what people sometimes call concrete cancer, this ASR reactions as an example of chemical reactions. And all that goes together and you have to set up a model. And so usually the models that you have are only of a certain accuracy compared to what reality is. Now, This is in terms of modeling, but on the other hand, there's lots of phenomena that are present on different scales. So usually people are interested in structural phenomena at that case here, a full-scale bridge. But many of the phenomena that you see macroscopically, they are related to very fine scale features. So what you see here is a lab scale experiment, and you see here fiber reinforced concrete in the middle. And then this is polypropylene fibers within the concrete specimen. And those are like responsible for the behavior under high temperatures. So in order to understand macroscopically what's happening, you might have to go to finer scales in order to understand that. On the other hand, there are these multi-scale phenomena in time, because we're usually interested in very long time safety issues, like we would like to have our bridges to be safe for a couple of 100 years. But there's lots of phenomena that interact. So if you have an impact of a car, a vehicle, that influences certainly the durability. You have fatigue issues, so a constant traffic changes that. But you'd also have phenomena that are very short timescales that you have to model by, for example, a molecular dynamics simulation. And so this is very challenging for modeling aspects, because you have to choose the correct timescales of interest, and you have to choose how to couple those in an appropriate way. What is also important are efficient simulation methods. And I want to go into the details here. This is just a model of an efficient fatigue model where you're interested in the durability of a material over time. And in order to avoid millions of cycles in a direct numerical simulation, you can perform so-called cycle jump methods in order to, say, extrapolate the fatigue behavior. Another very interesting idea is this model reduction. This is one example using the proper generalized decomposition. And so the idea is actually building a response surface for your models using all those parameters that you have of interest. We'll later see in an optimization procedure how that works. So usually you have, say, your displacement is the degrees of freedom in your finite element simulation. And then you're interested in I don't know, an optimization where you would like to change the Young's modulus, Poisson's ratio, strength criteria, whatsoever. And then for each of those parameter configurations, you'd have to redo your computation. And the idea of this PGD approximation here is to essentially build an abacus, so like a response surface, but it's a physics-based response surface based on this decomposition of your degrees of freedom, so your solution field, and you essentially compute a priori the response for all the different parameter configurations, and then you can use that in an efficient manner in the parameter identification procedure. It doesn't work for all problems, so the problem has to be separable, and it's a higher computational effort a priori. But if you then in the online phase where you use this response surfaces for model calibration purposes, it might save you a lot of time. Now let's come to model calibration questions or model updating. So this is a very simple example. What you see here is a tensile test. So this is the tension versus strain, and the slope of that curve is essentially a material parameter. What you see here on the right-hand side, this is a material parameter that gives you, at least in the elastic region, a very good approximation of the material response. Now, if you perform multiple of those tests, then the question is how reproducible is that test? So the uncertainty related to the test setup, the material, this is very important. The second question is, how good is your model? How is it applicable? So if you see that here, well, at the very beginning, this is a very good approximation, right? So in a linear case, this is very good. But at some point, if you exceed a certain threshold, then you see there's yielding of the metal for different structures. If you have concrete, and there's fracture phenomena happening. So what you would like to have is to understand what is your model bias and how good is your model applicable in certain regions. And if you then introduce a new model, what is also very interesting is to understand which model is better, because if you have the most complex model, that might not be the best one, because estimating those many parameters might not be possible with the limited number of data points. So there's always a trade-off between a very complex model that needs many parameters, and it's difficult to calibrate, but it's more expressive in the sense that it includes many different phenomena. And on the other hand, a more simple model that only has a few parameters that you can easily calibrate, but that certainly has then some limitations in the application phase. And that is always like a trade-off, and we have to identify which one is best. And I just want to show one example here. This is a problem people in our department and other departments solved. So this is a concrete specimen that you heat, and what you see here from the top, and you see high performance concrete without fibers, and you see at the top what is the moisture decrease. So the specimen is actually drying, and what you see on the right is the corresponding drying curve. So the moisture content, that's the reduction of the moisture content. So here this is almost zero, and you see here this is the drying front. Now we're then trying to model that, and so this is I don't want to go into the details here, but that's kind of partial differential equations that we set up in order to solve that problem. And you see here the comparison between measurement data and the numerical simulation. So the experimental data is the dotted line, and the solid ones are first guess of the numerical simulation. And you see there's a certain discrepancy here, right? And the question is, how do you change that? And so you can go there, perform more experiments, and then try to improve that. But the point is that you would like to know how good is my model and where should I change the model. And I think this is one crucial thing that we have to deal with in the future, that we not only try to reproduce a single experiment, but we try to make it general. And in order to make that general, we need many more data points. And that's something not only a single researcher can do, but that's something we as a community have to work on, that we share our data the way that other people can use our data to improve their models. And that in the end allows us also to compare different models with different data sets. And so this is how this model development cycle works. So we start with a certain model hypothesis that might be on a constitutive level that I just showed, but it might also be a structural model of, I don't know, a bridge, a car, whatever. And you set up the model, you perform some experiments in order to validate your model. Based on that, you get this experimental data, you simulate that, and then you somehow calibrate your numerical simulation and then validate the model and see if that's sufficiently accurate or if you have to improve that. Now, how do we do this model calibration? So in many cases, people just look at the data and then tweak and twist some of the parameters. Then you can go to an optimization procedure where you say, okay, I have a certain number of parameters and I have a certain set of outputs, and how do I optimize these parameters in order to reduce the discrepancy between numerical simulation and experiment? But that's always, I would say, very subjective, and it requires a lot of experience of the user. Now, what I suggest is that we also do not look into a deterministic approach, that you only look into a single set of material parameters that describe your forward model, but that we move to like a Bayesian model calibration. And so what is the idea here is you have some prior knowledge. So I know from experience, from previous experiments, what is the potential range of my material parameter. That could be, say, the Young's modulus of a concrete structure for concrete. So this is the prior, which is plotted here in blue, and then you perform some tests on specific cubes of that specific mixture that you've developed, and then you get more test data. And based on that you describe by a likelihood function, so you measure some somehow how accurate you can measure those compressive strength or whatever parameter you're interested in. And then based on that, you can put that into a Bayesian inference procedure, and you get something that we call a posterior. So that's kind of augmenting the prior distribution by data to get more information. And the advantage here is that you can actually take into account measurement accuracy, and you can take into account the uncertainty afterwards in performing, for example, a reliability analysis. So you don't only compute what is the the performance of a structure, but you could compute like a distribution. So how probable is that certain value? And for the computation of those, there's different procedures. One that's very common is using Markov chain Monte Carlo methods or similar approaches. They're very good, but they need many cases, many evaluations of the forward model. And this is where I discussed before, the application of reduced order models could be beneficial in order to improve that cycle here. So let me come to the last part of my presentation that's related to digital twins. And I would like to talk about the definition, the challenges, and then show you some examples on how this could benefit in industrial applications. Now, what is a digital twin? It's a virtual representation of a real physical asset, and the numerical simulation or the modeling part should represent the relevant features of the real asset. And that's, in many cases, it could be a finite element model or any other CFD model that you're interested in. It could also be an analytical expression. And what is important is, I would say that it's connected to the real asset via some sensor information. Now, the question is, how do you incorporate this sensor information into changes of your model? You could, for example, just measure, I don't know, forces, and then use those forces in, say, a fatigue analysis. So instead of using predicted or estimated, I don't know, traffic densities, you could use the direct loading that the structure has seen, and that might improve the structural performance computation. This is, I would say, the first level of a digital twin. But in many cases, as I just pointed out, your model is a priori, so the one that you started with, that's wrong in many cases, or it has, say, a model bias, so it has limited accuracy. So if you then add sensor data, you would see that there is a discrepancy even for, say, the undamaged state. And if you then want to use this digital twin for, say, damage identification procedures, for example, then it's of utmost important, from my point of view, to perform something like a model updating or a model calibration of your initial model that you use, and then continuously update during the lifetime or the monitoring phase. So where do I see the challenges when you would like to set up a digital twin? So the first one is the data in itself. So you have to acquire data that is of high quality, that is sufficient. So you have to select sensors the way that they're able to express or include the information you need in order to perform some model calibration, updating, or damage identification that's of interest. You have to process the data and get it from the site to your computer in the lab. You somehow have to store the data, and the question might be, how fast do I have to get it from the site to my lab? And as I said, the quality of the data is also of utmost importance. And in many cases, in particular in public funded research, FAIR principles have to be followed. So findable, accessible, interoperable, and reproducible. I would say many of those are also relevant for industrial applications because that's not only relevant for exchanging data with others, but also within, say, a company, those principles hold from my point of view. The second challenge is the simulation models. This is a famous quote from Box in 1987 that says, all models are wrong, but some are useful. And so as I pointed out, it's really important that we develop methods where we identify in a continuous way while doing this monitoring. We have to improve our models. And that's even more relevant in the case when we have many data points. So if you have just say a single load displacement curve, you can look at it and say, okay, at a certain threshold, there's something happening and I have to model an additional phenomena. Well, if you have a complex scenario, and usually the error is not where the model has to be changed, then it's very tricky to identify sensitive points in your model. And I would say that we need automatic procedures to support the engineer. And the last one is computational efficiency. So we can move to high performance computing and build even larger computers. But I think at the same time, we have to think about improved simulation methods that somehow simplify or increase the computational efficiency. We might use for these calibration procedures reduced order models or response surfaces. So I think there is a huge potential in combining physics-based models with data-driven models. I think that will come in the future. And as I said before, the third challenge is this calibration procedure. So you can start with manual tweak and twisting, you can do a least squares fit, or you can do a Bayes inference, but even there's lots of discussions of how you choose the model error, how you choose your prior knowledge. In many cases, that's, I would say, a little bit unclear. And what is also very important, and that actually covers the whole cycle that I was talking about, you have to make sure that your results are reproducible. So that not only includes the code or the compute environment, but it also includes how you get to this calibration procedure. So how do you actually perform this model updating? Because in many, say, publications, this is rarely discussed, at least in the presentations where people present their new numerical models. And I think this is of utmost importance in order to make those models usable for practical purposes, because only then people can understand the quality of those models. And what is also a challenge sometimes might be a real-time application. So there's always a benefit if you do it as fast as possible, but it might come with a lower accuracy model that you can use then. All right, now I would like to show you an example that we set up in order to show you a little bit what potential digital twin might look like. So we've set up here an example bridge in the lab. And you see here, there is a car that's passing over the bridge. This is this one here. We have a couple of sensors. So below here, you see laser sensors. They're at the bottom and measuring the vertical displacements at 6 positions. In addition, we have in the cables, I don't know if you see that, so those are cables here. We have force sensors that allow us to measure the forces within those cables. And then just for the lab, we have additional stereo camera. This is like these funny red dots that you see here with these patterns that allow us, based on the stereo camera system, to monitor the displacements in real time. So what you see here now is the real-time application. On the left top, you see the force, and below the displacement, so the laser sensors, and you see the identified position of the car compared to the real one at in the center. And on the left bottom, you see the identified car weight and the velocity. So this is just extracted from the data. We have measured that, but this is not used here. So this is an inverse procedure where we show, just based on measurement data, how we can introduce like a virtual sensor or some information that is not part of the experimental data. Now, what is a summary? So in order to set up a digital twin, it's really important that you think about the data acquisition system, processing and storage of the data, and also the structuring. So I think ontologies might help here to somehow structure the way that people can exchange that information. What is also important is that you include uncertainties. So I think it's an integral part of any digital twin is the inclusion of uncertainties in the model and in the data. And I think what's also very important, you need to have automated procedures to analyze discrepancies between models and data. So not only changing your model parameters, but trying to identify where the model is wrong and then help the engineer to, in a physics way, improve the model. But for complex models, as I pointed out, this is very tricky and we need automated procedures to do that. The fourth thing is that we need efficient simulation procedures to do everything in real time. Real time is, the question is what is real time, but in any case, we need for this model updating or model calibration, we need many forward model evaluations, and there it's really important to have efficient simulation procedures. And then finally, I would really point out that it's really important to have collaborative efforts if you want to set up a digital twin. So all of those challenges that I just mentioned here can't be solved by a single person, but you have to gather a team that with experts in different areas in order to set up that. So with that, I would like to thank you for your attention. And if you have questions, just send me an email and I'm happy to answer those.